So it's my pleasure to start the second talk of today, the Computational Adequacy for Substructural Lambda Calculi by Vladimir Zamdzhiev, I think.
Yes. Okay. Thank you. So I will talk about substructural lambda calculi. So first of all, what is a substructural lambda calculus? Well, Bert was talking about quantum programming and so on, and in particular, the type systems which are used there are usually linear or affine. Okay, so I'll explain this in more details, but first some applications. So linear and affine type systems, they have recently found applications in concurrency where they can be used to model session types for the P calculus, in quantum programming, which is what Bert was talking about until now, and also in circuit description languages, which is what Proto-Kuiper is about, for example. And they also have more traditionally found applications in classical programming languages where they can be used to model resource-sensitive data. Okay, so computational adequacy is a property of a type system, which says that its associated categorical model can be used to determine, to distinguish between terminating and non-terminating computation. So there is a complete characterization which is available there just by looking at the denotational semantics. And the reason that this is nice to have is that first they can be used to separate some of the models which are not so good, but also because you can actually use adequate models to reason about contextual equivalence, in a partial way. So to be able to reason more correctly for this, you will also need full abstraction, but having adequate models is an important step. And in this talk, I will discuss how we can determine whether a model, how we can construct adequate models for both linear type systems and for affine type systems in an abstract way. Okay, so first, I'll consider a simple linear and one linear and one affine type systems. So I will use x, y, and z to range over the variables of our calculus. And I'll use capital letters A, B, and C for the types. So we have a unit type, we have sum types, we have pair types, function types, and the bank here is used to, it's used for promotion. So it's the bank from linear logic. It's basically used to incorporate classical types into, or nonlinear types into the linear world. And we also have a subset of our types are nonlinear, so they're closed under formation of sum types and pair types, and again, the bank of any type we consider to be nonlinear. Okay, we have contexts, which I'll use gamma and sigma to range over arbitrary contexts, and nonlinear ones I'll use phi to range over the nonlinear contexts, which are just a list of variables associated with types. So for terms, we have variables, we have the unit value, value, left and right injections for some types. This is the rule for elimination of some types, or it's called pattern matching. We have pairs. This is the associated elimination rule. Lambda abstractions and application, lifting of a term, which corresponds to promotion, and we have we were allowed to force a term, which corresponds to dereliction in linear logic, and then we have a term for recursion. And now some of the terms are values, which are now defined by the grammar that we see here. Okay, so what's the difference between a linear type system and an affine one? So a linear type system imposes restrictions on the copying and the discarding of variables. So as an example, if we consider just a variable of type A, then it will be well formed in some context. So first of all, the context has to contain the variable x, obviously, and then the rest of the context has to be nonlinear. And similarly, the unit value is well formed, provided the context is nonlinear. Whereas an affine type system, it imposes restrictions only on copying, and that's it. So in this case, there is no restriction on what the context can be. Okay, so it could be an arbitrary context. So in quantum programming, for instance, this would mean that some of the unused variables would get discarded. Okay, so you have to trace them out. So in order to explain what's going on, I have a bit of a background on domain theory. So the previous speaker was talking about CPOs a lot, so I'm going to just quickly recap. So a CPO is a poset where every increasing chain has a supremum, and such a poset is said to be pointed if it also has a least element. And now a Scott continuous function between two CPOs is a monotone function that preserves the suprema, and if in addition the CPOs are pointed, then the function is said to be strict if it preserves the least elements of the CPOs. And now here there are two main categories of interest, which again the previous speaker also mentioned. So we have CPO, which is the category of CPOs and Scott continuous functions, and it's complete, co-complete, and Cartesian closed. And we have the category CPO bottom strict, which contains pointed CPOs and strict Scott continuous functions, which has a symmetric model structure. It's symmetric model closed, and it's also complete and co-complete. So basically, we will use CPOs in order to talk about recursion and also to axiomatize the adequate models. Right, so we are also interested in categories which are enriched over CPOs and pointed CPOs with strict maps. So what does this mean? Well, of course, you can just open like a book and read it, but in this specific case, it's very simple. So basically, a category is enriched over CPOs if the collection of morphisms from between two objects forms a CPO. And it's enriched over CPO bottom strict if this collection is also pointed. And then the other requirement is that composition is not just a function now, but it's a Scott continuous function. Okay, and enrichment over CPO bottom strict imposes the additional requirement that composition is also strict. So that's it. The other notions that are important is that of an enriched functor. So a CPO functor is again just a functor between the two categories in the ordinary sense. But now we require that this mapping here, which is usually, in the ordinary case, is just a function. Now here we require that it's a Scott continuous function. And enrichment over CPO bottom strict means that this function also has to be strict. And for natural transformations, well, the ordinary notion of a natural transformation coincides with the enriched ones in these two cases. Okay, another piece of background that it's also important to know when talking about recursion. So we will use the notion of algebraic compactness in order to model recursion in an abstract way. So this was introduced by Peter Freit. So basically what it means is that a functor is algebraically compact if it has an initial algebra whose inverse is its final coalgebra. Okay, so that's it. Okay, so the previous speaker was also talking a lot about linear nonlinear models. Well, I'm going to say a few words as well. So a linear nonlinear model is used to interpret type systems which have both linear and nonlinear features. And it's given by the following data. So you need a Cartesian closed category. Well, actually, in the original definition, the category is assumed to be Cartesian closed, but for our purposes, the closure is not so important. Yeah, we also assume that there exists finite coproducts to interpret subtypes. On the linear side, we assume we have a symmetric model closed category, which also has finite coproducts, and we have a symmetric model adjunction between the two. Now, because we're also interested in interpreting recursion, then what suffices is that you just have to assume that the bank comonad induced by the adjunction is an algebraically compact functor in a parametrized sense. So I'm going to ignore the parametry, what this means, because it's actually not so important for my talk. Okay, and this the notion was first introduced by Nick Benton. Okay, so what happens? So this is so the previous slide explains how to interpret linear type systems, but what about affine ones? Now here there is less research on the matter. There is some, of course. But the naive idea here is to just take a linear, nonlinear model and impose some extra structures, which explains how to discard how to discard information in general. Right. But now I'm interested in the question of how to construct a model of such an affine type system, which also has recursion and which is adequate. So if you use this naive approach, well, can you make it work? Well, the answer is no. So if you read the paper, I explain this. And well, more precisely, what's proven is that if you take a linear nonlinear model in the sense which I just formulated, which is sound, then if you interpret lambda abstractions in the usual way, which is by using the model closure of L, and you interpret recursion by either using algebraic compactness or order enrichment, then you can prove that this category here is completely degenerate. Okay, so it means that there is no hope of it means that the model is not adequate because you cannot distinguish anything. So that's the problem. What's the solution? Well, solution is actually not that much more complicated, but it requires, the main idea is to distinguish between the computations and the values. So the values are, basically the normal forms of the type system. And the computations are are terms. Okay, so what we do here, in order to do this, we have to assume now 3 categories instead of just 2. So we have B, which is a Cartesian category with finite coproducts. So here we can interpret the nonlinear values of our type system. We have another category V, which is where we will interpret the values, so whether they're linear or nonlinear. So we can interpret all values in here. We assume it to be symmetric monoidal, and we assume it also has finite coproducts. And finally, C, which is the category of computations, where we can actually interpret all terms, and we assume that it is symmetric monoidal and it has finite coproducts. In order to interpret the bang modality, we also assume that there is 2 symmetric monoidal adjunctions, which relate the above categorical data, which I just mentioned. And in order to interpret the lambda abstractions, now this is the important point here, is we use currying, which actually does not assume monoidal closure anywhere. So none of the categories here are assumed to be monoidal closed. So what we do is that the tensor product in V, when composed with the left adjoint L here, we assume that this composition has a right adjoint, which I denote with the wall pop here. But now you see that the right adjoint goes from C to V. This is because the lambda abstraction is always a value in a co-by-value semantics. Oh yeah, sorry, I forgot to say that I assume a co-by-value operational semantics here. Okay. And now if you're also interested in recursion, which, well, we are, then you have to assume that the comonad induced by the composition of the adjunctions is algebraically compact in a parameterized sense. So this model is inspired by work of Peter Selinger and Benoit Valeria. There are some differences, however, but the main idea can already be read off in that paper. But there they didn't consider the notion of adequacy, and there are some differences in how the bang is interpreted. And now this is more general than a linear nonlinear model, because in the special case where the category V and the category C are the same, well, then you get exactly an L&L model. So you get precisely the same thing. Okay, so it's a bit more general. So I just explained how we can now model a linear type system, but or a mixed linear nonlinear type system. But we're also interested in modeling affine ones. So now, as a second step to model an affine type system, it suffices to assume that that given the previous data on the previous slide, you just have to assume that the tensor unit of V is terminal. Because now this would mean that, well, here you always have the terminal map, which can discard anything. It would mean that all the values of your type system are now discardable. And this is exactly what we need if you consider the structure of the type system. Okay, so now it is possible to construct models which are not adequate. So to axiomatize, well, to provide sufficient conditions for adequacy, we need some additional structure. And this one will be described using domain theoretic techniques, which is pretty standard in the literature. So we will say that that one of our models is order-enriched if all of the categorical data that I've been talking so far is enriched over CPOs. And in addition, I assume that the computational category here, computational category C, is enriched over pointed CPOs with strict maps. And we will say that such a model is adequate if the additional, one further condition is satisfied, namely that the tensor unit of C is not the least element. Okay, so there must be something below the tensor unit of C. So that, and if these conditions are satisfied, then you can prove that the model is adequate. But to prove, before you can prove this, of course, you have to explain how to interpret your language in there. I'm not going to say, well, how to do everything, but because I only have time, but in order to interpret the types, what you need to do is a bit more complicated than in a, well, more traditional type system, because here you have to define the interpretation of types in 3 categories by simultaneous induction. Okay, and the reason that you, okay, so for the units, for the bang, and for the some types and pair types, it's pretty obvious what you need to do. I mean, there's not much to say here. Now, the reason that you need simultaneous induction is because of function spaces. So when you interpret function spaces in the computational category, you see here that you have to also know what is the interpretation as a value. Okay, so you take the value interpretation of A and together with the computational interpretation of B, and this itself is a value. And this is why you have to slap here the left adjoint in order to see this as a computation. Okay. And other than this, basically all the other ones are pretty clear. And terms, so arbitrary terms can be interpreted as morphisms in the computation. So I won't go into these details for it. Okay, and then if you do a bit more work, you can then prove that any such categorical model is sound, which means that the denotational interpretation of terms is invariant under program execution. This is both in the linear case and in the affine case. And any such model will be computationally adequate in the sense that, so in both the linear case and in the affine case. Which means that that the program would terminate if and only if its denotation is not the least element. Okay.
Vladimir, you are about to start on the question time. Okay.
Okay. Yeah, I'm basically done. So I have some concrete models. So the first one is completely degenerate. It's obviously not adequate. You just take the terminal category everywhere. And here I have 2 other models which are domain theoretic. So it's not a big surprise, but these are not very representative of our models because here you can copy and delete all values. More interesting, we have models based on W star algebras. This is something again that Bert was talking about. So but the issue there is that the model is not compact, so recursion is unclear. But this also gives a separation result here because we see that this category is not model closed. So we get something in addition to linear and nonlinear models. And finally, there are 2 additional concrete models that satisfy the abstract structure that I was describing here. Namely, a paper that we wrote with Mike and Bert in LIX 2018. And the recent quantum CPO model that Bert was just talking about in the previous talk. Okay, so that's everything I wanted to say. Thanks.
Thank you very much. Very, very interesting work. I think I've seen a question of Mike Mislov coming through the chat. I think he wants you to show something about slide 10. Mike, do you want to come in?
Yeah, I'm just curious, Barrett, you use the term compact for, sorry, Vladimir, you use the term for compact, and are you just referring to algebraic compactness there on slide 10?
Yeah, this means algebraic compactness here, yeah.
Okay.
So
Okay.
I couldn't come up with a better name. I could just rename it like a model with recursion, I guess, but then it seems kind of weird because it's a semantic property. It's a semantic property. So I just I meant compact in the sense of algebraic compactness. So
Okay.
in this sense here.
Yeah. Okay. Thanks.
Alex, you can go and ask your question.
Hi, Vladimir. Could you go to the slide where you gave the quantum example?
I have two quantum examples. So
The one
one
right
is,
at the end. Right at the, yeah, the one before, I think.
okay.
Yeah. So the values are multiplicative maps and the computations are CP maps. Is that what's going on here?
Yeah, so the value category is double-star algebras with normal, multiplicative, and involutive unital maps. Okay, so these are known as star homomorphisms. So Bert was talking about this in the previous talk, and these are normal, completely positive subunital maps.
Is there some intuition as to why it makes sense to think of one of those as a value and one of those as a computation?
What's the intuition? Well, in here you actually can't do that much, to be honest, right? So in W star and mu, you don't have. There are some operations which definitely you cannot do. And okay, I have a very good example. So here, for example, the scalars, you only have one scalar here in W star and mu, right? Mm-hmm. Whereas, and obviously, when you wish to talk about computation, or in particular quantum computation, then of course there's a lot of probabilistic effects which happen, and you want to be able to talk about the unit interval, right? So the unit interval lives in here, but not in here. So it's in C, but not in B. Okay. So this is why it's the V category is not a good it's not a good choice for computation.
Right. Do we have any other questions on the chat that I'm missing? I'm having a little bit of an issue here with some noise on my laptop. So, I think I have a question, but I think I will ask it in the Zulip channel after, because I need to discover what's going on with the noise here. So I just want to thank the speaker very much again.
Okay. Thank you.